Hello everyone, welcome to this lecture for GB 513. We are going to talk about the normal distribution in this lecture because it is a big part of what you do in Unit 2, but that's not all. Some of the stuff that you're going to be doing in Unit 3 when it comes to hypothesis testing also requires you to understand what happens with these normal distributions and how to look up z-scores and so on. So we have actually been building up to this. In the first unit, when you did the histogram, that forms the basis of how to look at normal distributions or any distribution in statistics in general. So you need to understand what a histogram shows you and what the heights of the bars mean and so on in order to be able to go forward. So that's what happened in Unit 1. In Unit 2, we are looking at the normal distribution, among other things. But that's what I'm going to focus on today because, like I said, it is going to be a building block for going forward. You also have to do some other probability-related calculations, but we're going to talk about normal distribution in this lecture. And then going forward is going to help you deal with some of the other stuff. One thing I would like to say about watching this lecture is that you need to have read the book before you start watching because I'm going to jump into a bunch of stuff and I'm going to assume that you have seen certain things. And if you have not read the book and if this is the first time you're watching, you're learning about the topic, you are going to be overwhelmed. Okay, a lot of things are going to be coming at you and you need to be familiar with it at least a little bit. So hopefully this lecture is going to clear up issues, but it's not actually going to teach you from scratch what everything is, because that's not something I can do in just a 40-45 minute video here. The other thing is when you're watching, feel free to pause all the time and try to answer the questions I'm asking or try to work out the numbers and so on. If you just watch it like a non-interactive experience, like watching a TV show, it's going to be really difficult for it all to stick. All right, so the more involved you get, the better it is going to be. If you have any questions, maybe you want to stop the video and write them down and email me the questions later on. But don't just watch it like a TV show and let it just wash over you because this is not simple stuff. And if you do that, at some point it's all going to start going over your head. All right, so let's take a look at the normal distribution. You are going to run into questions like the one that you see on the screen, not only in your assignment, but also in real life. Okay, you might see something like, this is taken directly from your assignment. According to a report by Scarborough Research, the average monthly household cellular phone bill is $73. Suppose the local monthly household cell phone bills are normally distributed with a standard deviation of $11.35. So that is the given information, that is the data. Then you can ask a whole bunch of questions like what is the probability that a randomly selected phone bill is less than $100? What is the probability that a randomly selected bill is between $70 and $90? And a whole bunch of other questions. Okay, so this is all based on three pieces of information. The first is that the bill amounts are normally distributed. The second is the average, the mean, is $73, and the third is the standard deviation is $11.35. Those three pieces of information allow you to go forward and do a whole bunch of analysis that is really useful. Okay, these are things that we would like to be able to figure out in real life. Sorry about that. All right, so this is all based on the normal distribution. Okay, a normal distribution, the name sometimes confuses people. It's not normal like a regular. A normal distribution is a formal name. Okay, it has a capital N. It could have been called a whole bunch of different things. They decided to call it normal, I guess, to confuse introductory level statistics students. But it's just like calling it a T distribution or a Poisson distribution or whatever. This is a formal name. Okay, it doesn't mean regular. All right, a normal distribution has certain properties that are useful to us. It looks like this that you see on the screen. Okay, so it has a bell-shaped curve. Let me grab a pen here. It has a bell-shaped curve. In a normal distribution, the mean the average, the mean is in the middle. Okay, so this is where the mean would be. This is, I'm trying to make a little mu here. That is the Greek letter for the mean. So the average is always in the middle in a normal distribution. And the normal distribution is symmetrical around the mean, which means that the right side of the mean, of the average, this side, is identical to this side. So why is that important? Why is that useful? Well, we can do things like this. Let's say the average, let's say we're looking at a distribution of weight, how much people weigh. Okay, and we figured out that the average weight in the sample that we took is 180 pounds. I'm trying to make an 8. There we go. I'm doing this with a mouse. I wish I had a touch screen or something. Anyway, let's say the average is 180 pounds. If the weights are normally distributed, then I can answer the following question. What percent of the population weighs more than 180 pounds? Okay, again, what percent of the population weighs more than 180 pounds? The answer is very simple. If the average is in the middle and the distribution is symmetrical around the mean, then 50% of the population will be higher than 180 pounds. So the easy follow-up question is, what percent of the population weighs less than 180 pounds in this scenario? And the answer to that is, of course, 50%. So it's this side, it's the left side over here. Okay, so the symmetrical nature allows us to answer at least this question easily. It's going to come in handy in just a second for other things too. Now, these are the same questions. The question, what percent of the population weighs more than 180 pounds, is the same as asking the following. If I picked a person at random, what is the probability that they would weigh more than 180 pounds? Let me see if I can type in here. I don't think I can type in here. Just give me a second. I haven't needed to type on these screens before, but all right. So let me repeat that again. Saying that, the question that what percent of the population weighs more than 180 pounds is the same question as asking what is the probability of getting somebody who weighs more than 180 pounds when we pick somebody at random. Okay, the answer to both of those questions are 50%. So if I pick a person at random, there is a 50% chance that they're going to come from this area. And if I pick a person at random, there's a 50% chance that they're going to come from this area. Why? Because 50% of the population is heavier than 180 pounds and 50% of the population is lighter than 180 pounds. All right, now we can do more interesting things than this. So we can ask other questions. Let's say this was the center of 180 pounds. We are not limited to asking questions like, what is the probability of getting somebody over the average and below the average? We can ask questions like, what is the probability in a normally distributed situation? What is the probability that a person picked at random weighs more than 200 pounds or 210 pounds? Or what is the probability of somebody that we pick at random weighs between 200 pounds and 220 pounds? Okay, so we can ask questions like that all the time. And these are not all that difficult to answer if you know the third piece of information that we talked about. In addition to knowing that this is normally distributed and knowing that the average is 180, you also know what the standard deviation is. And this is the letter sigma from Greek that denotes the standard deviation. Okay, let's say the standard deviation was 20 pounds. So the average is 180 pounds. The standard deviation is 20 pounds. And I can now ask a question where I say something like, what is the probability that if I pick a person at random, that they will weigh more than 200 pounds. So what is the probability that they will fall in this area? All right, which is another way of asking what percent of the population is in this area? What percent of the population weighs more than 200 pounds? If you know the distribution, which is normal, if you know the mean, which is 180, and if you know the standard deviation, which is 20, as given to us here, you can actually answer any kind of question about this distribution. All right, so let's move forward a little bit. Now, there are formulas that you can work through that will give you those answers. Okay, so here's the situation we were looking at. If I have a mean, which is 180 pounds, and a standard deviation, £20, okay, and I'm looking to see what percent of the population is heavier than 200 pounds. This is the question we were looking at just a second ago. Now, it turns out that all normal distributions are identical in terms of their properties. What does that mean? So this question of the weights is exactly the same question as the following. Let's say that the average income of a juggler, and I'm just making this up, is $60,000. It is normally distributed, let's say, and the average income of a juggler is $60,000 with a standard deviation of, let's say, $10,000. Okay? If I ask you the question, what is the probability that a juggler that we get at random makes more than $70,000? The answer to both the weight question and the juggler question is the same. Why is it the same? Because both questions are asking you basically this. What is the probability of getting somebody that is more than the mean plus one standard deviations? Okay, so look over to the weight side. If I ask you what is the probability of getting somebody that weighs 200 pounds or less, 200 pounds or more, that is basically the mean, 180 pounds, plus the standard deviation, plus one standard deviation, okay? And over here, if I ask you if a juggler makes, what is the probability that a juggler makes more than $70,000, that is also the same question where you are looking at the mean, $60,000, plus one standard deviation. Okay, so both of these questions are asking you the following. What is the probability that you're going to get somebody equal to or more than the average plus one standard deviation? I did that badly. I was trying to do one standard deviation right there. Okay, so both of these questions are asking you the same thing. What is the probability of finding somebody that is that falls in the area above the average plus one standard deviation? Okay, so like I said, if you wanted to, there are complicated formulas that allow you to work through any of these individually. But some people figured out that we can easily do this by looking at not at the actual numbers, but converting them into what is the average plus the standard deviation, which area are we looking at? Okay, so what they did was develop something that looks like this. All normal distributions have the same shape. All normal distributions are symmetrical around the mean. Here's the mean. Okay, so I can convert any of the problems that I get into the mean plus one standard deviation, the mean plus two standard deviations, and so on. The mean minus one standard deviation, the mean minus two standard deviations. So what they did was, instead of having to deal with the weight is 180 on the average plus 20 on the standard deviation, or the jugular is 60, or the telephone bill is $55 on average, blah, blah, blah. They just developed one single table that you can look things up. Okay? And since that single table cannot be done for any particular situation, you can't have a single table that covers both the weight and the juggling income and the telephone bills and all kinds of stuff. They developed that table for this basic layout. Okay, that table shows you all the probabilities for standard deviation around the mean. Okay, so let me show you what that table looks like. This is the table in your book that shows you probabilities. So look up here where it says, over here, where it says the entries in this table are the probabilities that a standard normal variable is between 0, which is the mean, okay, 0 is the center, and z, how many standard deviations out you are. All right, so a bunch of numbers in here. How are you going to read this table? This is actually pretty easy. Okay, if I want to know, I'm going to step back. If I want to know the probability of being in this area, if I want to know the probability of getting somebody outside or above or higher than the mean plus 1 standard deviation, remember this? The mean plus 1 standard deviation, which is this area. I need to look at the value for 1 standard deviation in that table. Here's how we do it. The z refers to how many standard deviations out you are looking at. Okay, the z-score refers to how many standard deviations you are moving away from the mean. So if I'm looking at the mean plus 1 standard deviation, my z-score is 1. Okay, so I go down this side, I find 1.0. This is how you look up the decimals. Okay, let me step back and explain how the table works. If you were looking at the mean plus half a standard deviation, 0.5 standard deviations, you would go, okay, I'm going to go over here, 0.5 standard deviations. Okay, and this will be the number that you're looking at. I'll tell you what that number is in just a second. If you were looking at, let me clear this. If you were looking at, for some reason, 0.33 over here, 0.33. If you were looking at being a third of a standard deviation out, okay, like that, then you would go, okay, 0.3 is over here, but what I want is 0.33, so I'm going to go 0.30, 0.31, 0.32, and 0.33. Okay, so the intersection of 0.3 and the 0.03, so this is the number that you would need. Okay, so that's how you read the table, because all the problems that you're going to see are not going to give you nice and neat 1 standard deviation, 2 standard deviations, 3 standard deviations. Sometimes you're going to have to look up 1.58 standard deviations. And if you have to look up 1.58 standard deviations, you would go, all right, 1.5 is over here. I go all the way across, and 0.8 is over here. So this is the number that I need over here. All right. So let's take a look at this. We have a situation that looks like this. Here is the normal distribution. The average is 180 pounds. The standard deviation is 20 pounds. And I want to figure out the number of people who weigh more than 200 pounds. Okay, so 200 pounds is the mean plus 1 standard deviation. So I come over here. All right there. That is the number that I need, 34%. Now look over at the instructions. 34% is the area that is between the mean and what you're looking at. So what this is telling me is that this area between the mean and one standard deviation is, this area is 34%. All right, so this is 34%. That's great, except that is not what I was looking for. I was looking to see what percentage of the people fall above 200 pounds. Well, I know this whole area to the right of the mean is 50%. We talked about this a few slides ago, okay? Because it's symmetrical around the mean sits right in the middle of the population. So if the whole area to the right is 50%, and this area over here is 34%, what does that mean for this area over in red? Then this area is going to be 50% minus 34%, which is 16%. Now, based on this, if I ask you this question, if I pick a person at random, what is the probability that they are going to weigh between 180 pounds and 200 pounds? What would be your answer? What is the probability that if I pick a person at random, they will weigh between 180 pounds and 200 pounds? The answer is 34%, because what we are looking at then, let me clear this up and draw it again. That's a bad normal distribution. If the average is 180 and the standard deviation is 20, so that 200 pounds over here is one standard deviation out. Okay, so this is one standard deviation out. And if I'm asking you, what is the amount of what is the percentage of people that fall between the average 180 pounds and 200, which is one standard deviation, then you're looking at this. Then the answer is 34%. You look at one standard deviations, we go over here, 34.13% is the area over here. Okay, so what is the percentage of people that fall between 180 and 200? 34%. What is the percentage of the population that falls over 200? It's the other side, it's this side, that's 16%. And I know it gets messy really easily. So let's do another example. Let's take the juggler. And this one is a little better. The juggler makes $60,000. Okay? The average is $60,000. His standard deviation is $10,000. What if I asked you what the probability is that a juggler makes more than $80,000? So the first thing we do is convert this into the standard shape and the z-score. $80,000 is 2 standard deviations out. 2 standard deviations out, right? It's 60,000 plus 1 standard deviation plus another standard deviation. So what I'm looking at is over here, 2 standard deviations out. And the question is asking about this area. What is the probability that they make more than $80,000? So the first thing I'm going to look up is the percentage of 2 standard deviations. Go down the z-score, get down to 2. It says for 2.0 standard deviations, it's 47% over here. Okay? And remember, by this shape over here, The 47% is the area between the mean. Maybe I should have changed colors there. It is the area between the mean and 2 standard deviations. So this area over here, this area is 47%. So what is the probability that they make more? Remember, the whole right side is 50%. If this area in here is 47%, then the area outside is going to be 3%. Okay, only 3% of the juggler population, based on these numbers, makes more. Only 3% make more than $80,000. And okay, now here's another question. Same question. What is the probability that when the average is $60,000 for a juggler and the standard deviation is 10, just like a second ago, what is the probability that a juggler makes less than $80,000? Okay. All right. So we start with the basic idea. The z-score is going to be 2. This is, we are looking at 2 standard deviations over here. Two standard deviations. Okay. Except this time we are not looking at the right side. We are looking at the left side. And we are looking at the entire left side. Okay. We are, since the question says, what is the probability that they make less than $80,000? That covers all the people over here. So how are we going to get that? Well, just like a second ago, we know that this population, based on this table over here, based on this graph, okay, this area that you see, just like here, between the average and the 2 standard deviations, this is 47%. Now, we also need to figure out what this part is going to be. Because when I say what percent of the population makes less than $80,000, we also include the people who are making less than the mean. All right. So what percent of the population is over on this side? And the answer to that is easy. That's 50%. Okay. Remember, half the population is on one side of the mean. The half population is on the other side of the mean. So what we know now is, and I have a little mess. The left side of the mean is 50%. The right side of the mean until 2 standard deviations is 47%. So the total population that makes less than $80,000 is 97%. Now you could have easily arrived at this answer from the previous question where we said this area was 3%. You could have just subtracted that from the entire population, which is 1.0. So 1.0, which, or 100% minus the 3% on the little tail end over there, that gets you 97%. Now, there is an interesting situation here. Let me just show you that really quickly. So let's look at the juggler again. Average of $60,000, standard deviation of 20. What is the probability that a juggler makes between, I'm sorry, this is 10, I said that wrong. The standard deviation was 10. I jumped ahead in my mind. The standard deviation is 10, right? Okay, so what is the probability that a juggler makes between $40,000 and $60,000? So the question is, turn it into a z-score. We are looking at this side now. $40,000 over here. And I'm asking about this area. What is the probability that they make between $40,000 and $60,000? Well, 40,000 is, as we know, $20,000 less than the average, which is 2 standard deviations. Just like a second ago. All right? But we are below 2 standard deviations. So instead of looking to the right, a plus 2 z-score, instead of looking at a plus 2 z-score, we are now looking at a minus 2 z-score. Because we are looking at the left side, these are lower. And this table does not have any negative numbers in it. Oh no, what are we going to do? Well, the key to this, the solution to this is in one of the fundamental properties of the normal distribution, which is that the the distribution is symmetrical around the mean. So whatever applies to the right of the mean is identical to what applies to the left of the mean. It's just that, you're subtracting the numbers instead of adding the numbers. So we still have to look at 2 standard deviations, except what we find now is not showing the right side. We are looking at the left side. We are looking at this side, okay? When we say minus 2 standard deviations. So the area then that is between 40 and 60 is going to be 47%. And that answers the question, what percent of the people make between $40,000 and $60,000? The answer is 47%. Okay? What percent of the people make less than $40,000? That is now asking this area. What percent of the people make less than $40,000? So if the right side of that is 47% and the whole area over here is 50%, then the answer is 3%. So the point of this last demonstration was to show you that it doesn't really matter if you're looking at the left side or the right side. As long as you keep your numbers straight, the table is the same. Okay, the table applies exactly the same way. The same amount of percentage of population is going to fall on either side of the mean because they are symmetrical. Now I will do one last one. This is the most complicated example that you're going to get. But it still works the same way. So let's look at the juggler again. And I hope you realize that the clothing that the problem is wearing does not matter. It could be a juggler, it could be the telephone bill, it could be weights. All I care about, what is the standard deviation and what is the mean? Okay, the story doesn't matter. All right, so what the question is going to be, if the juggler makes $60,000 on average and the standard deviation is $10,000, the question is going to be, what is the probability that he makes, a juggler chosen at random makes between $70,000 and $80,000. Okay, so here's the average, 60. 70 is over here. This is 1 standard deviation out. Okay, and then 80 is over here. This is 2 standard deviations out. So the question, if you take out the dressing, the question is basically asking you, what is the probability that a person chosen at random in this population, a person chosen at random makes between 1 and 2 standard deviations above the mean? Here's how we're going to figure this out. We are going to look at both of them and then take the difference. According to our chart, 2 standard deviations above the mean is 47%. So this area is 47%. Now what I need to figure out is, what is the difference between that and 1 standard deviation? That is a horrible looking normal distribution. It's difficult to do this with a mouse. So again, here's the average and here's one standard deviation. Okay? And one standard deviation, if you look over here, is 34%. So this area is 34%. So if you know that this area is 34% and this area is 47%, what is the difference? What is the area between them? And the answer is easy again. It's 47% minus, that is a 7. 47% minus 34% equals to 13%. So this is probably the most complicated that you're going to get. You might get something that where you have to look at something like, what is the probability of being 1.5% and minus 2% over here? But ultimately, they all work the same. Okay, you just have to find out the area in between, and you go about it piece by piece, like we did a second ago. If you don't like the table, people have worked out these breakdowns. So for example, this is taken from the web. The area between 0.5% is 19. Excuse me, 0.5 z-score is 19. Half and a 1 z-score is 15. So this comes out to 34, like we were talking about before. And here's what we just found out. The 13% between 1 and 2. So since they broke it up into half z-scores, 9 plus 4 is 13%, and so on. Okay, so as long as you take whatever average you are given and whatever standard deviation you are given, and you turn those into the standard z-scores, you can come back to this table and just look up the z values and then find out the area in between. And if you want this, you're good. If you want this, you wanted the area outside, then you have to do a little subtraction. But ultimately, it's just a matter of, moving numbers around, and you'll be able to figure out what you need. Okay, here's the last thing. The last question in your assignment says, a Travel Weekly International Air Transport Association survey asked business travelers about the purpose of their most recent business trip. Whatever. 19% responded that it was for an internal company visit. Suppose 950 business travelers are randomly selected. What is the probability that more than 25% of the business travelers say that the reason for their most recent business trip was an internal company visit? This might look like a completely different situation, but it's not. It looks like a completely different situation because there is no mention of an average or a standard deviation or a z-score. How are we going to get that? Well, it turns out that, I hope you read your chapters before watching this lecture. That's the best way of doing this, obviously, as we talked about before. Anyway, but as you have read in your readings, there is a simple formula to get the z-score you need. Okay, p hat is the number you are given for the problem. P is this percentage. N is the number of people who were polled over here. And Q is simply 1 minus P, which in this case would be 1 minus 0.19, which is 81%. So that's what Q is always, okay, 1 minus P. So that's it. It's just a simple formula. Plug all the numbers in and you get a z-score. Once you get the z-score, you can go back to this table. And if it's asking you, let's say the z-score turned out to be 1.23. Okay, this is where you might get this, strange numbers. If the z-score turned out to be 1.23, your value is 39%. Okay, so this is what you're looking at. This is the average. This is what you are looking at, 1.33, and this area is 39%. 39, oh gosh, that's a big 9. That's 39%, and you go from there. If it's asking you for this area, then it's 50% minus 39%. If it's asking you for the area in between, you got your answer. If it's asking you for all the people over here, and so on, you can just do your work. Okay, so ultimately, it looks like this is a whole different type of problem, but it's not. Once you get the z-score, you can just do it exactly like you were doing question number 2. And the other videos that we have go into more detail on how to solve these. So this is not the only place you're going to see this being solved. Okay, so this is all I have for today. I know it is difficult to take in when you're just listening to it, particularly if you're not trying to work through it with me. Okay, it's just a lot of stuff just coming at you very fast, and you know, this area, that area, all the numbers run in between, and all the colors get all scrambled up. But if you watch this video and you stop in the middle every time I ask a question and try to work out the numbers yourself, you will be able to understand what I'm saying a little bit better instead of watching it like a TV show. And working through examples always helps, and we have a whole bunch of examples for you, as you know, both in the shape of video examples and solved problems and so on. So I hope that works for you. Okay, well, I hope this was helpful. It sucks that, you know, we cannot be in front of each other and look at each other in the eyes and actually ask questions and so on, but this is the closest we can do. So that's, you know, we're trying to do the best of our situation. I will see you all in the Unit 3 seminar. I wish you the best of luck with this assignment and going forward. All right, have a wonderful day.